Assalamualaikum warahmatullahi wabarakatuh. Selamat sejahtera. Boleh dengar? Can you hear me?
Waalaikumsalam. Boleh, Prof.
Okay. Straight away, I go to the slides on the slide number 52. Okay. Can you see? So you are given the data. You are given a data as plotted in the graph shown below. Okay. So you have to determine the mathematical model based on the data plotted in the graph below. So this graph starts from 0, and then the final value is 2 volts. Okay. So from here, start from 0, meaning no time delay. Okay. So we're going to identify the mathematical model or transfer functions that fit the graph, the data that given. So the input is unit step 1 volt. Okay. And the transfer function can be determined by measuring the time constant from the graph. So time constant of the graph, as we know already, is the 63% of the final value. Okay, so 63% of the multiplied by 2 volts. Okay, which is equal to berapa? Can somebody help me? 63 over 100 multiplied by 2.
1.26.
1.26 volt. Okay. So first of all, you must understand the model structure. So the model structure of the unknown data is first order. Okay. So this is what we call as model structure. First order. Okay. Because it's power of 1. Then you have a pulse value. And you have a K. K is a gain. So value of A is we can get from the graph, okay, which is a 1.26 volt. So in this case, (1.26) is somewhere here. Okay, so it is about the time constant is about 0.0244 or 24.4 millisecond. Okay, so we insert the value 24.4 millisecond inside the T. Okay, then we will get 40.98, which is the value of the pulse. Okay, and then the final value can be calculated using this formula. Final value is equal to K divided by A. So the final value is 2 volt. A is 40.98. So therefore you will get K, which is equal to A multiplied by final value 40.98 multiplied by 2 volts. So the K value is 81.97 over S plus 40.98. So this is what I call as estimated transfer function based on the calculations from the graph. So we use this, insert inside the MATLAB. Okay. Okay, step G, then you get the same graph, okay, which is the time constant is 0.0244 at amplitude 1.26. Okay, settling time 0.0955, and final value is 2 volts. Okay, so verify. Second example, you are given a data which is shown here. Okay. Okay. So from this data, you are required to find the estimated transfer functions. Okay. So from this graph, based on our knowledge, okay. So what do we observe? Okay. So it is a second order system. Okay. Is a under dam category. Under dam category. Time delay 0. Okay, time delay 0. What else? What else? Second order under dam, time delay 0. So you have to find the, I guess you have to find the overshoot, which will give you zeta. Then you have to find the settling time. You will get omega n. Okay, sorry, omega n. Omega n and omega d, I guess. Okay. Then find the k. Okay, the k value. Right. So from here, okay. So this is the data. Then we start to measure the overshoot percentage and settling time from the graph. Okay, so first we have to find the final value. So the final value is about 11.03. Okay, and then you have to find the maximums amplitude. So the maximum amplitude is about 13.82. Okay. Right. And then from here, you can find overshoot. Okay, which is overshoot is equal to maximum amplitude minus final value divided by final value. So 13.82 minus 11.03 divided by 11.03 multiplied by 100, 25.3%. And the settling time is plus minus 2% of the final value. Okay, will give you about 2.62 seconds. It roughly is about here. Okay. So we estimate this as a second order system because the shape is second order under category of underdamped response. Okay, so the zeta is 0.4. This is from overshoot of 25.3%. Okay, so how do we get zeta 0.4 from 25.3%? Okay, it is just using this formula. There are three ways. First is using formula where you insert the 25.3 in here. Okay, then use a natural logarithm. Okay, so pi is 3.14, so you get the zeta 0.4. Or you just can use what do you call that? The graph. Okay, the graph, which is remember the graph? This graph. This graph. 25.3. Okay. This here goes down. Lebih kurang still, which will give you 0.4 zeta. Okay. Or you can use this formula. Okay. That formula, which is here. Exponent minus okay. Right, okay, negative. Right, so this is a 25.3% exponent. So can change like this. 0.253, right? Then how are we going to simplify this? Is applying natural logarithm left and right. Okay. Natural logarithm 0.253. Okay. Can somebody help me? Natural logarithm 0.253. Somebody, please. Natural logarithm 0.253.
Negative 1.374.
Negative 1.374.
374.
Okay. So this one, since this one is natural logarithm and this is exponent, you can bring it to the left. And this natural logarithm e is 1. Okay. So cancel out negative. So you can find, you simplify, so you can get zeta is equal to 0.4. Right? Ada faham? Understand?
Paham, Prof.
Okay, so 0.4, then use the settling time where you already given there. You already get it from the graph 2.62. So simplify omega n. Okay. So you will get omega n is equal to, okay, 3.82. So now you know omega n, you know zeta, and yet you have to find the gain k. So the model structure for second order system is here. Okay, this is the model structure. Okay, and the final value is 11.03, which is equal to k divided by omega n squared. So omega n is equal to 3.82. So 11.03 multiplied by 3.82. So you will get k is equal to 161, which is here. Okay. So you insert the omega n value and 2 zeta omega n. This one is 2 zeta omega n. And of course, this one is omega n squared. Okay. So you get 161 plus 3.1 and 14.6 second order. So insert inside MATLAB, S, EF, insert the G, and then plot step G. Then you will get same value as okay, as with the data. You can compare lah. This is your estimated. Estimated. Compare with real data. Real data tu apa? Real data is this one. This is real data.
Excuse me, Prof.
Yes.
Hello, this if we have the ripple, we can find the zeta because we have the C max and C final.
Yeah.
So what if the graph is second order and doesn't have the ripple? It just like the first order one, you know, like exponential graph,
Yeah.
but it is second order.
So you have to observe the second order categories. This one. Siapa yang tanya tadi? Ashraf
Yes, Prof. Betul.
So under them response starting from 0.1 till 0.8, you can see that 0.8 is under them, but there is no overshoot. Nampak tak? 0.8.
Nampak, Prof.
So I think your category is something like that.
Ah.
0.8, 0.6. So the overshoot is
Yes.
not obvious.
But can we just assume the zeta equals to 1 if we
You
get the graph
to
like that?
calculate first. You have to calculate first.
Okay.
You can try and error lah. You assume, then you generate the data, then you compare with the real one.
Excuse me, but how do we find the overshoot?
Huh? Overshoot. In this case, there is
Yeah,
no overshoot.
0.
In this case, there is no overshoot.
So how does it get 0.8?
0.1, 0.5, 0.6 maybe lah. Ada. Above
Hmm.
0.6, there is no overshoot.
So how does it get the zeta value? Because if we want the zeta value, we need to have the overshoot.
Compare with the real data. Compare with the standard. This one. Compare with this one. The graph. You compare with this standard second order second graph. Then you can estimate the zeta. It's not wrong if you estimate zeta 0.7, 0.8, 0.75, and so on, because you need to get the zeta value so that you can insert in the model structure.
Okay, Prof. So far, so good. Thank you.
So we continue to the second one, the third one, which is this one. Okay. So this one also, by observations, is a second order. Final value, 1 volt. Cmax, 1.4. Peak time, 4 seconds. Okay. So this time around, we use the same approach. Okay. Overshoot, which is 40%. Okay. So damping ratio of, from this 40%, by using graph and formula, you will get zeta 0.3. The peak time from the graph is 4 seconds. So we know that peak time is pi divided by omega d. Omega d is equal to omega n square root 1 minus zeta square. Okay, so from here, since we know that the peak time is 4 seconds, so that's why omega n is equal to pi 4 multiply 1 minus 0.28 square. Okay, so you will get omega n as 0.818, and zeta is 0.28. Okay, final value, which is equal to k divided by omega n square. Okay, so k is the gain. Final value is 1 multiplied by omega n, 818 square, so you will get 0.669. Okay, so you insert k here, omega n here, and zeta here, so you will get the estimated transfer functions, 0.7 s square plus 0.46 s plus 0.7. And the validations, compare with the real one. Okay, it's about the same. Okay, where final value 1, settling time 16.9, but we don't use settling time here. We use a peak time. Okay, so you can get the mathematical model. Okay, I would like you to try for extra, okay, go to your, I give you in your WhatsApp. WhatsApp. Okay. Estimated three model data below. Okay. Okay. T1, T2, okay, and T3. Okay. T1, T2, and T3. Right. So we continue on the slide. Okay. The variation of zeta, omega n, omega d, Tp, and Ts, plus the overshoot percentage, where you can see that if the complex conjugate poles, okay, pattern, okay, so if you have a complex conjugate pole 1, 2, and 3 towards the upper side of the S-plane, going up and going down. So the response shape is shown in this figure A, okay? And you can see that the common factor between these three pair of complex conjugate pole variations is will give you the same envelope, okay? Same envelope of the exponentials. But if the complex conjugate poles is moving towards the left of the left half plane, far away from the imaginary axis, you can see that the shape of the response is similar at the peak level where the frequency is the same, okay? But if the pair of the complex conjugate moving towards diagonal, okay? This one is vertical. This one is horizontal. And this one is a diagonal movement. Okay, diagonal movement of the complex conjugate pole. So it will give you a different peak time and settling time, but the overshoot is the same. Okay, so that is the pattern of the complex conjugate pole movements. Okay, in the rest time response. Look at these examples where you are given a block diagram, okay, of a unit step 1 volt. Then the system output response is plotted in Q22, which is here, same like your assignment. Based on the response curve, find the values of overshoot, damping ratio, omega n, and the values of A and K. Okay. So K is the gain. Gain. Okay. And A is the value of the coefficients of the S. And this system is type 0. Okay. Because, sorry, type 0, type 1. Okay. Because it is S power of 1. Okay. So from this graph, you can find the C final or final value, which is equal to 1 volt. And C max, which is equal to 1.2 volt. Okay. And the peak time is equal to 2.5 seconds. Okay. So the model structure for open loop transfer function is K over S ES plus 1. Then if you apply a closed loop transfer function, so it becomes K over ES square plus S plus K. So you simplify so that S square is alone. Okay, there is no coefficients value there. So it will become K over A S square 1 over A plus K over A. Because we want to compare these simplified transfer functions to the second order standard, which is omega n square over S square plus 2 zeta omega S plus omega n square. So from the overshoots, 1.2 minus 1 divided by 1 will give a 20%. And from this 20%, use this formula, so you will get zeta 0.46. Using a peak time formula, so you will get omega n 14.1.42 radian per second. So you have the parameters value now, zeta and omega n. So you compare, okay, you insert inside, okay, 2.02 as omega n square, which is 1.42 square, okay. Then you compare with this, okay, K divided by A. Okay, so 1 over A is equal to 1.3, which is here. So you get A 0.77 and K divided by A is equal to 2.02. So you will get K 1.56. Okay. And to verify K divided by A, you will get 2.02. So you insert this estimated transfer functions, okay, and then you compare with the real one, is about the same. So in assignment, you have to show the real data, which is represented by red circle, okay, and the blue one is the estimated data. So you compare two graphs in one using Excel. System with the additional pools, 4.5. So by using assumptions, 5 times a rule of thumb, broadly accurate guide of principles based on the experience or practice rather than theory. Okay, we are using a rule of thumb. If we have a high order system, we have a case 1, case 2, and case 3. So case 3 is a second order, pure. Okay. Case 2 is a second order approximation. And case 1 is a pure third order. So most of the assignment given is a third order. Your assignment model structure, most of them are third order system. And it is represented by this response. Okay, case 1, case 2, and case 3. Oops. Okay, so you can see that C1 is the pure third order system. C2 is the third order but second order approximation or assumptions. And C3 is the second order. Okay, so you can see the difference there. Okay, between C1, C2, and C3. So when the system is considered as third order, when the system is considered as second order approximations. Okay, so you are given the 3 transfer functions, T1, T2, and T3. Okay, as shown in the WhatsApp. Okay, T1, T2, and T3. So you have to find the response, okay, the time response, and then you can see that the third pole, okay, which is if the third pole is near to the imaginary axis, okay, so it is considered as a third order system. But if the third order is far away from the imaginary axis, so you can consider it as a second order approximations. For example, in this case, okay, so can somebody help me find these roots? S squared plus 4s plus 100. Can somebody help me to find the roots?
-2 plus minus 9.8 J.
J9, eh?
Yes, 9.8.
Then this one is 15. Now listen. Microphone off, please.
Sorry.
So, dengar sini, listen to me very carefully. Okay, what is the real part of complex conjugate poles? Real part. -2 kan? This one, eh? -2, eh? And what is the third pole value? Third pole value is -15. So the ratio -15 divided by -2, how much? 7.5, which is greater than 5. So if greater than 5, meaning that we use the rule of thumb just now. Okay, so kita pakai 5 times. Okay, rule of thumb said 5 times. So in this case, the ratio is 7.5, and it is greater than 5. So meaning that this GS is second order approximation. Okay, and we can ignore the effect of third order because it's far away from the imaginary axis. Let's go to the second part with GS. Okay. Okay, somebody help me to find these roots.
-1 plus minus 9.4.
J 9.4 minus J 9.4, eh? And then the third pole is -4. Okay. So you can see that the complex conjugate pole, CCP, is -1 plus minus J 9.4. And the real part value, -1. Okay, third pole is equal to -4. And the ratio, which is -4 divided by -1, which is equal to 4, which is less than 5. The first one just now, greater than 5, but this one, less than 5. So rule of thumb said, if 5 and below, so this one is considered as a pure third order transfer functions. Okay, so it's not second order transfer function because s plus 4 is near to the imaginary axis and have a high influence and high effect towards the system. Okay, so that's why, okay, that's why the answer for this problem is shown here. Okay. Second order approximation is valid due to ratio is 7.5 greater than 5. This one is not valid due to ratio is 4, which is less than 5. Understand? Okay. So okay, so we stop here. Wednesday, we go for steady state error. Any question?
Doctor,
Yeah.
like our assignment, we are third order, right? How do we decide second order approximation to valid ke tak if we're not given with the third pole, like our assignment?
So you have to calculate and estimate the third pole first. Okay. Your transfer function is second order with complex conjugate poles with the third pole. So you try to play around the value of third pole given until your estimated data follow the real data.
Okay, Doctor.
Okay, is there any questions?
Yes, Prof.
Yes, please.
So you mentioned earlier about the graph, that we need to plot it in one graph. So when we get the mathematical equation, so how to make it in Excel? I don't get that part.
You don't get that part. What, which part?
Question 4, in the procedure, plot the real or measure data and estimated simulated data together in one graph in Excel.
Have you plot your data?
Yes.
Can you share?
Wait. Can you see it? Oh. Wait. His hand. Suddenly. Okay. Allah. Yeah, bro.
I nampak black bull ya. Okay. So besarkan sikit graph ni. Okay. So this is real data. This is from my data, am I right?
Yes, correct.
So better you print or you estimate from here. Ni group berapa ni? What group
Group
is it?
6.
Ah,
G6.
group 6 eh?
Ah.
Okay.
Uh-huh.
So what is the problem?
The problem is after get the mathematical equation, we need to make the this is the real data, the estimated data. Yeah.
Okay.
So then it tells us to group 6.
Group 6 eh?
Yeah. Okay, bro.
Yeah.
So we got the mathematical equation, then we've plot on the MATLAB, but the procedure tell us to make it on the Excel. So I'm so confused about that. How can I make a graph using Excel, using Laplace equation? Yeah, it's right.
First you find the settling time. Sharp.
Okay. Yes.
Then you estimate zeta.
Mm-hmm.
Your zeta ni about 0.8.
Okay.
And find the second order as a function.
Mm-hmm.
Your system ni is third order.
Uh-huh.
Your system is third order.
Third order.
Third order.
Okay. All right.
No complex conjugate pole.
Okay.
All are real pole.
No, yeah, real pole.
And 1 zeros.
1 zeros.
So they are the 1 zeros at the numerator, and at the bottom you have 3 real pole. No complex conjugate pole. So you can try Ashraf.
Yes.
S plus 5 over S plus 6 multiply S plus 11 multiply S plus 19. Simple lah. Can you
So
repeat what I say just now?
no bro, I'm
Can you
clear.
repeat?
Kan I tak sempat nak salin.
Tak sempat lah ni. Mana you punya group Video
Ada. Prof, my question is on the procedure number 4 actually.
Okay lah. So,
Mhm.
from this graph, your model
Mhm.
structure is, tadi apa I cakap?
Apa dia?
Your model structure just now. Cantik tak tadi? Apa yang I cakap?
Third order. 1 poles, three poles,
1 zeros,
1 zeros.
3 real poles.
Yeah.
Just now, I asked you to write the transfer function s plus apa tadi? S plus 5.
Mhm.
Okay. Divide
Okay.
s plus 6. Multiply
Mhm.
s plus 11. Multiply s plus 19.
Okay.
Sebut-sebut.
S plus 5 over S plus 6 times S plus 11 times S plus 19.
So that is the estimation from this data. Estimate je,
Okay.
belum lagi. So you type in your MATLAB.
Mhm.
Type in your MATLAB and then you generate the time and output data from that MATLAB. Sample or program in the questions at the bottom.
Oh, we can generate the output and time.
You follow the questions. Can you share the questions? Your question.
Okay. Yes.
Kat bawah tu, kat bawah tu. The bottom one. Sample for times response data generation. So you type lah G tu yang I bagi tu.
Mhm.
And Y open square bracket Y space T close square bracket equal to step G then step G.
Oh, okay.
Then you get 2 column of data which is T is the time, Y is the output. Then you copy paste lah side by side with the real data that I give you.
Okay. Faham.
Boleh?
Boleh bro. Thank you.
Kau ni tak baca soalan habis.
Saya
Baca
tak
sampai
nampak.
habis.
Saya tak nampak YT. Okay, thank you bro. Sorry.
YT. Siapa lagi yang tanya soalan? Any question? Any question? Group 3? Kata nak tu. Okay, if there is no question, we end the sessions. Then group 3 can click again the link after 5 minutes. Again.
Okay.
Bagi toilet.
Okay, Doctor.
Thank you.